Hello, good morning. So far we have learnt some single step methods to solve initial value problems. So, it would be better to work out some exercises in order to get the flavor of each of the methods and feel more confident. Okay. So, let us do some problems. So, this tutorial is on tutorial on single step methods. Okay. So, better to have your calculator with you and then start working with me. Okay. So, this is problem 1. Compute an approximation to y of 1, y dash of 1 and y double dash of 1 using Taylor's series method. Of order 2 with h equals to 1 when y x is the solution of So, let us read the problem carefully. Compute an approximations to y of 1, y dash of 1 and y double dash of 1 using Taylor series method of order 2 with h equals to 1 when y x is the solution of the following initial value problem. Look at that, this is third order. Okay. So, hence we have 1, 2, 3, 3 initial conditions all at. So, we have x 0 is 0, h is 1. Well, I have taken h is 1 just for computational ease. Okay. Okay. So, now we are asking to compute approximations for y of 1, which is y 1, y dashed of 1. So, y 1 dashed, y double of 1. Okay. So, these are to be computed, right. So, look at the it is to be computed using Taylor series. Suppose y of 1, that is y 1. So, we know usual Taylor series expansion, but then how do we compute y dash of 1 and y double of 1 along similar lines as it will be done for y of 1. Okay. So, let us have a look at that. Okay. So, Taylor series of second order, Taylor series of order 2. Okay. So, this is y 1, this is y 0, y 0 prime h square by y 0 double. Okay. So, given data, given y of 0 y dash of 0 y double of 0. So, therefore, y 0 dashed y 0 double we have. So, hence y 1 can be easily computed. So, this is 0, h is 1 to y dashed, y 0 dashed is 1 plus h square by 2 factorial. Okay. So, therefore, this is 1 there 2. Okay. So, now what is next to be computed? So, y 1 we have computed. Now, we have to compute y 1 prime. Okay. So, how do we do it? So, let us write down the series, Taylor series of order 2 for y 1 prime. Okay. So, y 1 prime is, so this is equals y 0 prime plus, so it is like y 1 prime. So, let y 1 prime equals to z. So, then for z of 1 we write it and replace it. Okay. So, same thing we are doing. Okay. So, this is our expression, but given what? The given data so this is the given data. Okay. So, in order to compute y 1 prime we need y 0 triple, which we do not have, but we know that y is a solution of the given ODE, right. So, also given so this implies y 3 equals to minus 2 y double minus y prime plus y. Okay. Therefore, y 3 of 0 1 minus 2 y double is okay, minus y 1 y 0 will be 0. Okay. So, this is minus 4. Okay. So, now we are in a position to compute this one. Hence, this is y 0 prime is 1. So, 1 h y 0 double prime is 2 1 square by 2 y 0 triple prime. Okay. So, this is y 3 y dash of 1, this is minus 2 and this is 2 get cancelled and this will be 1. Okay. So, we got approximation y dash of 1. Okay. So, now y double dash of 1. Okay. So, Taylor series for this. Okay. So, now we do not know y 4, okay, but given from the ODE we have computed So, from here y 4 so therefore, y 4 of 0 is y 3 of 0, just now we have computed y 3 of 0 minus 4 y 2 of 0 y dashed. So, this is this is 7, hence y 0 double 2, this is y 3 is minus 4, y 4 is 7. So, this will be okay. So, using second order Taylor series, we have obtained approximations to y of 1, y dash of 1, y double dash of 1. Okay. So, all that we have done is we made use of the given having known that y x is solution of this ODE, we have computed the higher order derivatives. Suppose you have to compute y 4 of 1, then we differentiate this further and try to obtain higher order derivatives. Okay. Right. Okay. So, let us proceed further. Given the initial value problem y dashed equals to x minus y square, y of 0 x 1, if the error in y of x obtained from the first four terms of the Taylor series is to be less than okay. So, let us try to understand. Given the initial value problem, if the error in y of x obtained from the first four terms of Taylor series is to be less than, that means you obtain y of x and if the error has to be less than this, then what should be the condition on x? Okay. So, first four terms means we have to compute up to y 4, right. So, that means y of x obtained from first four terms. Okay. So, this is y of 0 plus h sorry x plus x square by 2 factorial plus Okay, right. Taylor series method, first 1 2 3 4, first 5, let us make it 5. So, that is plus x 4 by 4 factorial, okay, 1 2 3 4 5, first 5 terms. So, we need to compute the higher order derivatives. Okay. So, y 0 equals to 1, y 0 dash equals to x 0 minus y 0 square. So, that is 0 minus 1. Okay. Then y 0 double. So, that is 1 minus, okay, evaluated at. So, this will be 1 minus 2, y 0 is 1, y dash is minus 1, okay. Then y 0 3 is minus 2, y dash square, of course evaluated at. So, this will be 1, y 0 is 1 and y 2, so this is 3. So, this will be then y 0 4, so this will be 2, y dash is minus 1, y 2 is 3 plus y dash is minus 1, 3, so this will be okay. So, therefore, y of x is, we have written already y 0 plus x y dash 0. So, by substituting we get 1 minus x plus 3 by 2 x square minus 4 by 3 x cube minus 7 by 12 x 4. So, this is using first 5 terms. Okay. Now, if this is the case, then what would be the error? So, the error y 5 x is minus 2 okay. So, this is y 4. So, y 5 so this will be okay. So, this is 3 there. So, 3 y 2 plus y dash 3 plus y 3 plus y dash y. Okay. So, this is the, so this will be minus 2, 3 plus this is 3 and 4 times, y dash is minus 1, y 3 is minus 8. So, this is 1, y 4 is 34. So, y 5. So, therefore, the error this is minus 2 times 93 by 5 factorial. So, this is 2 times 93 by so this is equals to 31 by 20 and given, not given, it is required that mod T 5 must be less than or equals to point this much. This implies 31 by 20 must be less than or equals to, it is slightly difficult to solve, but then one obtains the estimate. So, this is the range of x. Okay. So, let us try to understand what we have done. We have given initial value problem. If we use the first 5 terms, so first 5 terms of the Taylor series is to be is used, and if the error on using first 5 terms is to be less than this, find the range of x. So, what did we do? So, first 5 terms goes up here, hence the error come from T 5, that is from the 5th term, as the 6th term, and that needs to be less than this. So, on solving we obtain the corresponding estimate. Okay. So, this is how we find out the corresponding estimates. Okay. So, now problem 3, apply Euler-Cauchy method with the step size h to the IVP okay. Apply Euler-Cauchy method with step size h to this IVP and determine an explicit expression for y n for what values of h the sequence y n is bounded. Okay. So, what the method says, apply Euler-Cauchy method with step size h, okay, to this initial value problem. Determine an explicit expression for y n, okay, and for what values of h the sequence y n is bounded. So, when we determine expression, then b part is trivial. Okay. So, how do we proceed? So, first let us write down Euler-Cauchy method. Okay. Euler-Cauchy method. So, this is Euler-Cauchy method. Okay. So, now we have to use this method and determine the solution y n. Okay. So, for the IVP, f of x y is minus y. Okay. So, therefore, k 1 equals this, k 2 is so this is nothing but minus y n plus h k 1. So, this is minus y n, k 1 is minus y n. So, minus h y n. Okay. So, therefore, y n plus 1 is y n plus h by 2, k 1 is this plus k 2. So, minus y n minus h 1. So, this will be, so this is one coefficient here and so 1 and minus 2 and 2 get cancelled. So, minus h, then this is plus h square by 2 y n. Okay. So, what did we get? Y n plus 1 is 1 minus h. Okay. Right. So, y 1 is y 0, y 1. Recursively, if we apply y 0, okay, hence y n is y 0, okay, n is from 1 to. Okay. So, this is an expression. So, a part is done. Now, for the b part, for what values of h So, the sequence y n is bounded. So, this is the sequence is bounded if and only if mod 1 minus h is less than or equals to 1. This implies, so this is the range for which the sequence is bounded. Okay. Right. So, such methods will give an idea how to compute the boundedness of the solution and the range on the step size. Okay. So, we have simply applied on this method and then try to determine the solution y n explicitly and then put the condition for boundedness. Okay. So, let us move further. Okay. Find the region of absolute stability for the Hans method, okay, given by okay, where k 1 is this, k 2 is okay, k 3 is okay. Find the region of absolute stability for Hans method. Okay. So, now what do we do for absolute stability? There is a reference equation. So, we have to consider only the corresponding reference equation. Okay. So, what will be that? So, the reference equation is y dash equals to lambda y. Okay. So, the reference equation is y dash equals to lambda y. Okay. So, let us work out k 1 is f of x n y n, which is lambda y n. K 2 is so this will be lambda times y n plus h by 3 k 1 is okay. So, this is lambda 1 plus okay, then k 3 So, this will be lambda K2. K2 is so this will be lambda 1 plus 2 by 3 h lambda plus 2 square y n. Okay. So, therefore, is y n plus h by 4. This method is k 1 plus 3 k 3. Okay. So, k 1 is lambda y n, 3 k 3, k 3 is this much. So, 3 lambda y n 1 plus okay. So, this is simplified 1 plus lambda h by 4 okay. So, now this is exactly E of lambda h y n, where E of lambda h equals 1 plus lambda h plus this okay. Now, for absolute stability, so this implies so this is okay. So, this implies lambda h belongs to, so it is pretty tough, but one can solve it. Okay. So, this is the interval of absolute stability. Okay. So, for example, if we some possible values. So, for example, if h is of course always positive. So, we if lambda is positive, then lambda h. So, whatever may be the value positive. Okay. So, if it is beyond this, then it is not admissible value. Okay. So, lambda equals to say minus 1. So, this gives absolute stable. Okay. So, one can obtain various values. Okay. Right. So, then let us consider. So, this is P 5 or this is P 5. Okay. So, consider consider the method y n plus 1 equals to y n plus h f n plus 1. Okay. So, this is almost looking like Euler, but this is called backward Euler. Okay. Consider the backward Euler method and find the region of stability. So, the method is again straightforward. So, the reference equation is okay. So, therefore, the reference equation is this. Therefore, y n plus 1 is plus h lambda y n plus 1. Okay. Right. So, we need to get a form, right. So, how do we get it? 1 minus this equals y n. So, this implies, so this will be okay, right. So, therefore, E of lambda h is this, okay, right. So, now for absolute stability, okay. So, we had E of lambda h is 1 minus lambda h for absolute stability, okay. So, we need this, okay. When, so this condition, so we have to come up with a range. So, before we arrive at the range, so we can argue when lambda is positive what happens, lambda negative what happens, and things like that. When lambda is real and lambda is negative, okay, lambda is negative, okay, then see if lambda is negative. So, h is positive, if lambda is negative. So, this becomes 1 plus lambda h. Okay. So, this 1 over of that is then is true always. Okay. So, therefore, the method is absolutely stable for minus infinity lambda h 0, okay, right. But the other case lambda can be complex as well, okay. When lambda is complex, okay, with real part of lambda less than 0, say, so lambda is complex, real part is this, then so this quantity is less than 1, we need, okay, or 1 minus lambda h greater than 1. So, this gives 1 minus x square y square greater than 1, okay, right. So, what is this region? This is the region outside the circle with center at 1 0, okay. So, this is the region and radius 1, okay. So, depending on the problem we arrive at different stability conditions, okay. But for a given problem, how do you come across lambda, okay. See, f is nonlinear. So, f can be any nonlinear quantity, but then the linearization says you can linearize it and then figure out what is f, okay. So, for example, if y dashed is say x square plus y, so this is our f of x y, okay. So, then our lambda is dou f by dou y. So, in this case it is just 1, okay. Suppose y dashed is x square minus y square. So, then lambda is minus 2 y, okay. So, now suppose we would like to analyze, right, about the point 0 1, then lambda is minus 2, okay. So, for example, if you are using Euler method, right. So, when you are using Euler method, what kind of h will give us, okay, so that the method is absolutely stable. So, for this, keeping this lambda in view for this initial value problem, we have to choose h such that the range of the absolute stability interval is met, okay. So, these are some observations we have to be careful about, okay. So, now let us look at another problem, okay. So, this is a RK second order, okay. Consider the Runge-Kutta second order method, okay, given by equals to y n plus okay, k 1 is well, if you take h there, we need not, otherwise we have to take h here. K 2 is so x n plus this is alpha h beta k 1. Okay. So, if this is the case, okay, find the region of absolute stability. Okay. So, the story is the same. So, now consider the reference equation y dashed equals to lambda y. This implies this. So, k 1 is h lambda y. Okay. So, then k 2 k 2 is h so this is h into lambda y n plus, so this is lambda h y n plus beta k 1. So, that will be lambda h beta y n. Okay. So, this will be 1 plus lambda h beta y n. Okay. So, therefore, y n plus 1 is, this was our y n plus 1, this was our y n plus 1. So, y n plus 1 minus k 1. So, k 1 was lambda h y n plus 1 by 2 beta k 2 lambda h 1 plus lambda h beta y n. Okay. So, this can be written as 1 plus lambda h, we take common, okay, 1 minus plus lambda h by 2 beta 1 plus lambda h beta. Okay. Yes, this is right. Okay. So, from here we have to obtain what is E of lambda h. Okay. E of lambda h. So, consider a special case. Okay. So, choosing alpha equals to beta 1 plus okay, at least in this case. So, we get 1 plus lambda h plus into y n. Okay, this is a special case, otherwise you get very complicated expressions. So, we have to get the range of the interval will consist of alpha and beta and lambda h. Okay. So, at least in this case it gets simplified. So, therefore, E of lambda h is 1 plus lambda h plus lambda square. Okay. So, for absolute stability mod this must be less than equal to 1. Okay. So, this is satisfied when lambda h belongs to minus 2 0. Okay. So, that means, if say h is 1/4, so lambda equals to say 3, the method is not absolutely stable, because it is minus 2, right. Suppose h is half and lambda equals to minus 2, then the method is absolutely stable. Okay. So, estimating these stability intervals is very much useful. So, that there is a trade off between the lambda and then step size, and in turn lambda depends on the given nonlinear function. Okay. So, maybe next class we will do some more problems. Okay. Until then, thank you. Bye.